Greetings. My name is Scott Gould. I'm a professor of physics at the Claremont Colleges in Claremont, California. The talk is based on my experience for the last 20 years of using and teaching Maple in my physics classrooms, particularly for the last 6 years. I'm trying to get students totally immersed in Maple. Let's get started. So the title of my talk is What Sells, What Frustrates in Teaching Maple to Undergraduates. Let's begin. My intended audience here are those of you who are instructors at undergraduate institutions who might be doing applied mathematics in your discipline. I'm going to assume that your students have had exposure up through calculus, maybe linear algebra, differential equations. There's no need for them to be an expert on coding at all. In fact, the whole goal here is that many of the students will not have a lot of experience with coding. So we're trying to use Maple in its least complex form. The goal here is to sell a paradigm shift that Maple is not just a powerful mathematical tool environment, but it is a fully interactive educational and presentation environment. All right, what sells? We have to start initially with worksheet or document. Here is worksheet mode. It has the execution groups. It has the text groups. Here is document mode. Same thing. Unfortunately, students have a tendency to forget to put something in, so they had to add a new execution group. This adds to a couple problems here. Not a big deal, but what's the biggest problem is now that we have text, non-executable math, and math, sometimes they will put a lot of code in non-executable math. This will lead to more frustration. Generally, document mode causes frustration. Worksheet mode sells. Keep the math in the execution group, the text in the text group. Maple input versus 2D input. Generally, students early on, they see the problem like this as a differential equation. Therefore, if they want to use Maple 1D input, they're going to try to type it like this. This happens all the time, or maybe like this, or maybe, and this happens quite a bit, is to try to essentially reproduce exactly what they see as a 2D derivative. If you use 1D mode, then you have to teach them how to use functions such as diff command and maybe even some terminology such as the repeater symbol. 2D input works as you see it. 2D input is so much smarter. It even does the D operator without having to teach them how to use the D or operator. My answer is 2D input tends to be less frustrating. It will, by seeing what you write, sells. In fact, a 2D input has become so smart that things such as what I used to have to use as the add function becomes just a sum symbol. So here's an example of doing a Fourier series approximation of a function, for example. These two produce exactly the same output. Okay. What sells is writing math. B of n colon equals 1 over n, not B as a entity takes n and maps it in. Okay. I even have a PhD in math colleague who says he will not use Maple, would not use Maple until they move to the f of n or f of x definition. So as I said, low activation barrier to generate input or readable input. Students love subscripts, atomic variables. Treat them carefully, but they love them. They love vector signs. They love the fact that Maple does symbolic calculations. They like the fact that generally they're down to a single command for solving functions, although there are some problems. They like documentation capabilities. They like adding numbers and page numbers. Most of the students at the end of the semester for my classes are literally just turning in nothing but the Maple document. If they write anything in scratch paper, they've taken a picture, load it to the Maple document. So it's just the document. Here's a classic example of what students like to see because it's very readable to them and it's easy for them to generate. Here is a differential equation. In fact, these are two differential equations. They involve taking the time derivative with respect to time. That means the dot notation. It is of the vectors. Maple is now smart enough to break this up into vectors and figure out to take the derivative with respect to time. The requirements necessary to solve it are really fairly simple now, just the equations necessary in the problem. However, this does lead to some problems. They have to extract out the solutions. This often leads to difficulties. Why aren't the solutions returned by Maple already immediately assigned to x of t and y of t? In addition, when they get an expression, they can't just simply say r of t is equal to this expression. They have to use the most unintuitively named function in Maple, known as the unapply function. They get frustrated with the fact that it comes out very complex, and they are constantly having to be reminded that they should simplify the results, assuming positive. So what frustrates is definitely the big number one frustration I have with students is they get an expression as a solution, and they can't immediately turn it into a function without basically multiple function commands. They do have some problems with the occasional unseen white space. They certainly have the issue at the temporal versus spatial execution, in that they will enter this finally and then realize they made a mistake up here, re-enter this one, and then jump down to there. That's been a problem. I'm hoping that Learn and Flow will solve this problem here. There are still some minor frustrations. The lack of simplification really isn't that a big of a deal, but it does cause some problems. This may be a frustration, but the truth is it allows you to teach the difference between what is equate, which says everything on the left-hand side does not depend upon what's on the right-hand side. They are just two different entities, okay, that are always equivalent to each other regardless of the situation, versus assign what is on the right-hand side is exactly what we mean by what's on the left-hand side when we, as a symbolic representation. There's a buried solve function in BD tools. Bring it out, please. Students have problems. Why not? Why do we have a solve and a dsolve and a PD solve? They also have problems in terms of distinguishing between solve and fsolve. If there is a floating point number, I'm wondering if it's useful to turn the problem into an fsolve problem, and so that there could be only one function known as solve. Premature evaluation or lack of full evaluation can be a problem. We can talk more about that. But surprisingly, one of the biggest problems there used to be, which was Weisbeat rules for imports in terms of making sure that the parentheses was directly next to a function and not putting a space between the end of the function name and the opening parentheses in 2D math, has been solved by putting the dots. So that problem has basically disappeared. Okay. Here's something you can use to really convince your students that they want to use Maple. Go to Tools, Tutors, Single Variable Calculus, Integration Methods, and you will get this tutor, which basically shows how to integrate the, in this particular case, sine of x squared. Okay. It will provide the hints, and you can go through step by step to show what steps are necessary. The reality is you'll probably end up pushing all steps, and you will hear a collective groan by the students who realize that the days, hours and days that they spent on doing these types of problem solving could have been solved within a few seconds using Maple. I've even done this with my colleagues. Here's a problem that a colleague said that they had a potential as shown on the surface here. This blue dot represents an equilibrium point of a depression. The red dot is the origin. Basically, we want to push a body along the XY plane and have it essentially oscillate about the blue dot. She went around the whole process by basically doing a small perturbation approximation, then diagonalizing the matrices of the ODs, extracting resonant frequencies, and eventually writing some code in Mathematica. It went through pages and pages of notation. I wrote that solved the problem in 5 lines with no handwritten calculations. She now changes how she changes the types of problems and the types of solution approaches, because it just isn't worth doing all this work. I've also had another colleague who said she filled an entire whiteboard trying to solve a problem that Maple solved in 1 line. So what sells? Certainly being able to do 2D plots, certainly being able to do 3D plots, certainly being able to put 3D plots on top of plots, and basically having these plots based on a single equation, which is based on a single principle. Plots that are difficult to visualize are easiest to see. They love the colors. I mean, who else? Who doesn't love XKCD Booger? Shadings, arrows, and again, the ability to display combinations of plots. My suggestion is solve all or essentially end all problems on exams or even on your homework sets where a plot has to be generated. You'll be able to tell whether the students were able to generate what was going on or whether they have no idea where they're headed. Animation certainly sells, whether it's in 2D, such as the dancing stars, or whether it's 3D, involved charge inducing a magnetic field. And finally, the biggest thing that sells is probably the explore function, because it allows us to create little apps. Here's an example of light passing through a double slit. Okay, here are the functions that they get out of the textbook that they can plot. Okay. And so they do plot the function, but by using the explore function, they can pick up a series of parameters that they can vary, which will therefore change this plot. This is very useful for me in terms of saying, okay, I want you to create an explore function so that you can teach someone else how to visualize what's going on here. But often, they say, oh, what I'll do is I will make a plot. But the plot, again, is a perspective of recognizing that where it's high is a white spot and where the function is low is a black spot, when they can actually do the same thing, again, using the explore function with a density plot. And this is the type of image that they see when they shine light through two small open slits. Again, allowing them to change the parameters. So not only reproducing a mathematical representation of this physical phenomenon, but actually essentially reproducing the observation of the physical phenomenon itself. The last thing that they do that is very useful is taking advantage of the parameter option if you're solving a problem numerically. A lot of functions or a lot of problems in physics can only be solved numerically. Here's an example of a swinging Atwood's machine. So the idea here is these two masses are connected by a rope. This mass has more mass than this mass, but what we're going to do is we're going to give this mass basically a pull, allow it to swing back and forth. Because it's swinging, there is additional tension on the rope. So even though this has less mass, it can generate more force and therefore lift up the red mass. Reproducing the ODEs that are used to essentially mimic the motion of the position, the radial position and the radial angle of the blue mass. The key here is same equations, and we can set up parameters. Alpha will be the multiplier of the large mass to the small mass. Theta naught is our initial angle at which we're going to release the small mass. And then it goes dsolve using these params. There's our numeric. And then the other thing I strongly encourage, which students find more successful, is to use the output equals list procedure, because it creates functions that they're used to, which they can then plot. They can do anything with and they just treat it just like any other function. They don't need to learn another function such as ODE plot. So when they explore a trajectory with two different parameters, alpha and theta naught. Here they are, our parameters. It sends it to a small procedure. The students are comfortable writing very small procedures, which changes the solutions for that particular parameter of dsolve, and therefore allows us to plot. And so they don't have to go back and recalculate dsolve with different sets of angles. They can change different sets of parameter values, different sets of constants. They can do it on the fly. Because in the end, the best way to learn is to teach. And what I found that in getting students to use Maple as a tool to teach content to their colleagues, to their fellow students, they are more interested in what they're doing. They're more excited. Everything you have seen in this presentation, with the exception actually of this image right here, was all created by students. I did do some cleaning up. Okay. And with that, let's take a look here. Are there frustrations? Yes, the Maple interface still has some problems, menus that fails to display, execution groups sometimes will not execute or move to the next group. The error statements still tend to be, although they're better, difficult or impossible to interpret. Magenta is a terrible color to see. Maple Help is getting better, but still too many pages are too detailed. There are too many options when you do a search return, and a number of the examples include too much knowledge of Maple. There doesn't seem to be consistency there. That said, again, Maple Help has improved. I'm hoping it continues to improve. I do actually prefer MATLAB Help. Context panel, I'm not a fan of it. Its problem is beyond a handful of problems. The concept of using the right menus or the context panel, the right button menus, the context manual, is that it eventually you run into limitations. There's no context panel option for like Explore or anything like that. Eventually you have to write code. So I have not found context panel useful. In addition, it has a tendency to sort of leave the answer hanging. And therefore I've actually seen students copy and paste from answers of the context panels into their next execution group. And copying and paste is not the way we should be doing it. The Maple portal has gotten much better. Unfortunately, it's still dedicated to the context panel paradigm. And for my own personal objection is the PDF generator still has some problems, lots of problems. Okay, if you are interested in protocols on how to teach Maple, this is what I've ended up doing on my own. I use Maple operations as a natural choice for solving problems, particularly if they realize everything is easier with Maple. Okay, I maximize the use of palettes, maximize trying to get things to look like math, and minimize the number of functions. When I work with Maple in class, early in the semester, I lead them through line by line. They like that. I sometimes have to walk around the room, seeing what they're doing, find errors. Once they see a common error, it could be as simple as forgetting to put a semicolon at the end of the line. They get it. Later, we can actually reduce ourselves to doing the occasional demonstration how to solve a more complex example, and eventually you can just simply hand out solutions in class. But early on, leading them line by line is very useful to generating confidence in what they're doing. Okay, I have no problems touching their code. Some computer science faculty members said it's unacceptable. And of course, the key is get them to generate their own projects, get them to generate their own Maple worksheets that solve something of interest on their own. And with that, thank you very much. And I will now take your questions, if there are questions to take.